Everything in natural language processing completely changed when recurrence was replaced by one incredibly powerful concept: self-attention. It's the absolute heart of the transformer architecture. In this explainer, we're going to build this mechanism from the ground up, but we're going to keep it focused strictly on its simplest form: a single attention head. We'll break down exactly what problem it solves, the specific matrices that drive it, the precise formula that brings it to life, and two deeply surprising properties about its structure that actually dictate how the rest of the model is built.
To understand why this mechanism even exists, we really need to look at a fundamental problem with fixed word embeddings. Think about it. A word's meaning fundamentally depends on its neighbors. Take the phrase bank near river and compare it with bank near money. If we're only relying on a raw embedding, the vector for the word bank is exactly the same in both of those sentences. That raw embedding just cannot capture the difference in context on its own. We desperately need a mechanism where each word actively looks around at the rest of the sentence and updates itself based on what's actually relevant. We need active context.
And that is exactly what self-attention delivers. Let's define it simply. Self-attention is a mechanism where every word in a sequence attends to every other word in that exact same sequence. And yes, that includes itself. It's basically asking, of all the words in this sentence, which ones should I actually pay attention to and by how much? It's a lot like individuals in a group discussion. Before anyone speaks, each person listens to everyone else and weighs what they heard. Some contributions matter a lot to them, others not at all. Then they form their own updated view. Self-attention is literally every word doing that simultaneously to form a completely new, context-aware representation.
To execute this, the mechanism relies on three matrices with very specific roles. We call them Q, K, and V. But here's the real secret of bare, single-head self-attention. At the very start, Q, K, and V are just identical copies of the exact same input matrix. Seriously, for a 6-word sentence, they all begin as the exact same matrix of word vectors. So, if they're the exact same data, why do we give them 3 different names? Well, it's because they play 3 distinctly different roles in the calculation.
We can actually understand these distinct roles through a database lookup analogy. The 3 names are query, key, and value. The query is the asker. It's the word saying, hey, here's what I am looking for. The key is the label, what each word offers, saying, here is what I represent. And the value is the actual content, saying, here is the information I will hand over if you attend to me. Think of a search bar. Your typed search request is the query, the result tags or titles it matches against are the keys, and the actual page content you click through to read, that's the value. In self-attention, the exact same set of words simultaneously acts as the askers, the labels being matched, and the content being retrieved.
All of those roles come together in one single line. This is arguably the most famous equation in modern AI. Attention of Q, K, and V equals the softmax of Q times K transposed divided by the square root of dk, all multiplied by V. Now, looking at that as one big block of math can definitely seem intimidating, but I promise it's not a complex math problem. It's just a really logical flow of information.
We can break this famous equation down into a really rhythmic 4-step sequence. Step 1 is to score. Step 2 is to scale. Step 3 is to soften, and step 4 is to blend. Score, scale, soften, blend. Once you master that rhythm, the entire mechanism becomes totally digestible. Let's walk through them one by one.
Step 1 is to score. We multiply the query matrix by the key transpose matrix. What this actually does in practice is calculate a dot product. That's just a mathematical measurement of similarity for every single word's query against every single word's key. For our 6-word sentence, multiplying these gives us a 6x6 grid of raw attention scores. This grid simply measures how related every single word pair is. So row 3, column 5 literally answers the exact question, how much does word 3 relate to word 5?
Step 2 is to scale for stability. We take that entire grid of raw scores and divide it by the square root of dk. That's the dimension of the keys. Why do we do this? Because when dimensions are large, the dot products in our raw scores grid grow massively large in magnitude. Large numbers are a real problem because they push the next step into a region where learning stalls and gradients vanish. Dividing by the square root of the key dimension acts as a necessary stabilizer, keeping all of these raw scores within a sane, workable range.
Step 3 is to soften, and this brings us to the softmax function. Softmax is a mathematical function we apply row-wise across our scaled grid. It takes those raw attention scores and turns them into positive weights that sum to exactly 1. It's very much like percentages. A word's row of raw scores transforms into a clean distribution of attention over the whole sentence.
It might say a word spends 60% of its attention on word 5, 30% on word 2, and 10% elsewhere. Step 4 completes our rhythm. We blend. We take those newly softened weight rows and multiply them by V, the value matrix. This blends the information exactly according to the weights we just assigned. So if a word puts 60% of its attention on the word river, it pulls in 60% of river's value vector. Each word's final output becomes a weighted sum of all the value vectors, yielding a newly enriched, highly context-aware vector for every single word in the sequence.
To really solidify this entire formula, imagine mixing a playlist by votes. First, everyone scores every song. That is our Q times K transposed. Then, you normalize those votes so they sum to exactly 100%. That's our softmax step. Finally, the final mix plays each song in exact proportion to its share of the vote. That is multiplying by V. The loud favorites absolutely dominate the mix, and the ignored tracks barely even register. Score, scale, soften, blend.
Beyond these core mechanics, there are two intrinsic design properties of this Baire formula. And these aren't just fun trivia. These two facts dictate the architecture of the rest of the model and completely explain why the transformer is built the way it is.
The first crucial property is that in its Baire form, self-attention contains absolutely zero learned parameters. Look back at the formula we just walked through. It is literally just matrix multiplications, a division, and a softmax. If Q, K, and V start as direct copies of the input, there is absolutely nothing in this mechanism to train. It consists entirely of pure structure. There are no tunable knobs. This is exactly why, in the full model, learned weight matrices must be added later to transform the input into Q, K, and V.
Property 2 is a concept called permutation equivariance. This means that if you shuffle the input words, the output comes out shuffled in the exact same way, without changing the attached values for each word. The mechanism itself is completely order blind. Think of it like reordering people in a group photo. If you shuffle where people stand, it doesn't change their individual faces or the information they carry, they've just moved position. If you shuffle the input to self-attention, each word's computed representation just follows it, totally unchanged in value.
Because of permutation equivariance, a phrase like dog bit man is treated identically to man bit dog by the Baire attention mechanism. It just sees the exact same words in a different order. It basically treats the sentence as a set of words, rather than a sequence. This strict order blindness is exactly why positional encoding had to exist. Attention is deliberately order blind for the sake of symmetry and efficiency, so positional encoding is injected later to restore the sequence order that this mechanism ignores by design.
So, we've covered the core process. Every word becomes a query, key, and value. We score the pairs, scale them for stability, soften them into percentages, and blend the values into new context-aware vectors. And we've seen it operates with pure structure and complete order blindness. But this brings us to a massive final thought. A single attention head produces just one set of relationships, but human language is endlessly rich. A word relates to others grammatically, semantically, by tense, all at the same time. If one attention head captures one type of relationship, what happens if we run several in parallel, each free to focus on a completely different kind of connection?